So the next speaker is Andrew. So he is from Vietnam, and he is currently finishing a PhD in the School of Information Systems. Let's welcome Andrew.
Okay, so I will try to be quick because I know that you are all excited to go to the demos. So the study I want to present today is about multi-perspective Graph-Theoretic similarity measure. So basically it's similarity learning. So I will start by example. So if you look at these pictures, so can you tell which two items are more similar? Is it the T-shirt and the high heel are more similar? Or the high heel and the sports shoe are more similar? Yeah, so my point here is that you base on different attribute or different aspects of the item, then you have different similarity comparisons. So if you base on the color, then the T-shirt and the high heel are more similar as compared to the green one sports shoe, right? But if you base on the categories of the items, then these two are more similar. And interestingly, if you base on the occasion in which you wear these items together, then the T-shirt and the sports shoe should go better fit each other. So the question I want to ask and find the answer is how to tell when two items are similar according to what perspective. A perspective here could be an aspect or a concept, or could be an user, because we are not really the same. So we are all different, so we have different perspectives. Yeah, so that is a recent question. So a couple of challenges when we want to answer this question is that as the observation of similarities of a perspective maybe under sample. Like you don't have the observation about all the objects, let's say all the items or all the images. And yeah, two objects may be similar to one perspective, but could be different according to another perspective. So how do we take these two challenges into account? Yeah, that's a fun example, right? So which picture is more similar to picture A, B, or C? How many of you think it's B? Okay, so 2, right? So the rest think C? Okay, yeah, that makes sense, right? Yeah, so here comes the model, right? So let's say we have two perspectives here. I call it P1, P2, right? And we have 4 objects. So let's say the situation is that according to perspective 1, object 1 is more similar to object 4, the object 2 is more similar to object 3. Whereas according to perspective 2, then object 1 is more similar to 2, and 3 and 4 are more similar to each other. A couple of notation, right? You have object nodes, and you have some perspective graph, in which you have an edge to connect similar objects. So the problem is that given multiple graphs representing multiple perspectives of the similarity between objects, how do you measure how similar the objects are according to one perspective? So we quantify this according to this variable, which is the similarity between, let's say, object I and object J according to one perspective P. And we normalize it to be a value between 0 and 1. So it's like how certain you are about how these two objects are similar to each other. Yeah, so this is the input, and what we want to measure is this variable. So a couple of, so what people have been working on in the literature is that they have a model called SimRank. So simply SimRank, you are given a graph, and you need to measure how two graph nodes, how similar two graph nodes are. So ignoring the math, right, the underlying principle of SimRank is that two graph nodes are similar if they are referenced to or by two other similar nodes. It's like friends network. We are similar because we have similar friends. So then SimRank will produce similarity score for any two nodes in the graph. So we think of a way, how can we use SimRank to do our problem, to solve our problem. So this is our multiple similarity graph, right? The simplest way is that you just use SimRank for each of these graphs directly, so that you can produce a similarity measure for each perspective. But we think that the potential drawback of this approach is that because you learn from each perspective independently, so there is no information sharing among the perspectives. And because we don't have observation of all the objects, so without information sharing, it could downgrade the performance of the model. So another approach is that why don't we just combine everything we have from all the perspectives, and we run a SimRank model on this merged graph to produce a single shared score between of similarity between objects, and this could be shared by all the perspectives. So this one, the drawback is that you cannot express a specific view of one particular perspective. It's like you cannot show that you are different from another perspective. So then we propose an approach which is we want to learn collaboratively. We learn from multiple perspectives simultaneously. Meanwhile, we still want to allow one perspective to be specific so that they can express their own view. So then first step is that we kind of merge all of these graphs together, but we still maintain the perspective in this picture. So you can see that in this merged graph, right, you have perspective nodes and you have object nodes. So according to one's perspective, if the two objects are similar, then you have head to edge that connect the perspective and the two objects that they think they are similar. And the way we measure it is that, so given a perspective P and two objects I and J, you first look at other perspectives and you want to see how this perspective thinks these two objects are similar. And then you weighted by the similarity between the perspective and another perspective. So it's like you want to look at your friends and you want to see how they think the two objects are similar. And you also want to see how similar you and your friend are. And then you average out by like these values. So then you come up with how you perceive how two objects are similar. Yeah, so the question is that we need to quantify these two values, right? So the first solution is that we measure the similarity between two perspectives, and we also use Preferred.AI which is a variant of SimRank. And after SimRank, you can measure how similar two perspectives are, and then you run the previous equation iteratively until the algorithm converges. So this is the first solution. The second solution is that we do update these two values simultaneously. So at the same time, you update how you learn that you and your friend how similar you two are, and at the same time you update how you perceive the two objects as similar. Okay, so to validate the hypothesis that we have in this study, we explore 3 different data sets that could vary model the varying similarity perceptions among the objects. So for the conventional way of testing the model is that we split the data that we observe in for training, we learn the similarity between objects, and then we test the performance on the testing data. And the two evaluation metric we use is recall. We try to recall the object that we hide during the splitting, and we measure based on how well they can recall the correct hidden objects. And then another metric is to basically try to estimate how well the model can rank the hidden object among all the available objects. Basically, these two score, the higher value, the better the performance. So I'm just going to show the performance of all the models for one data set. So this is a recall value, and the two models in the hot colors basically show better performances in terms of recalling the hidden objects based on the similarity that they measure, that they learn from the training data. Similar picture you can observe for the second metric. So this is to say that by modeling both similarities between two perspectives and similarity between objects according to one particular perspective, you can actually evaluate the performance of how you can quantify how two objects are similar according to one perspective. So to conclude, we propose in this study a graph-based framework that can measure how two objects are similar according to various perspectives. And we validate the framework with 3 different data sets. So potential application, especially in context of recommendation system, is that sometimes you have user can clusters, let's say items, e-commerce items into baskets when they shop online, or when they go to a website like YouTube or Spotify, they create some playlists. So these are different collection, different cluster that they think these objects and these items are similar or related. So by learning how different users perceive the relatedness between items, you can actually recommend other items to current playlist of the user. We try to expand the current playlist to improve the user experience. So that could be the potential application of this study. So if you are interested, you can take a look at our implementation and our paper, which is available online. Thank you very much.